I will learn to do that.
Well, no, don't worry. It's very easy.
So Alan is not coming because he spent his girlfriend is here until just tomorrow.
Oh,
Because she was here for the first month and now she's back because she's a graduate student in Paris. So they took a weekend to Montreal.
Wow.
Ah,
They
There
missed,
is
oh,
and a lot
but
of snow in Montreal.
there was not as much snow. It was just normal. Only 15.
Well, that's better if they were still here.
Yes.
yeah, in Montreal, that's romantic, right? Just have some snow and
Let her know that apparently in Montreal they don't get spooked by snow as easy as here. So
So if you want, on Wednesday, there's a professor from Bologna, Marco Lenci, that is doing a like a seminar, but more a kind of informal seminar to introduce the topic for ergodic theory and mostly for infinite ergodic measure systems. If you want, from 2 to 3 in 6180. So he
What?
6180. So he claims that it would be like introductory, so like for also
For
for
us.
yes, also for
that's
the
good.
people that are not using like what
It sounds interesting. But what time did you say it was? It's
it's Wednesday 2 to 3.
Hmm.
And there is 6183, and like close to that, there's a small one that is 611.
Is the cost of
Of Jacopo De Simoi and Giovanni, also the postdoc.
He's going to teach in Italian?
No.
well, I'm going to miss the first one at least. Probably most of. We have a reading group that we do online at precisely that time. So either I change that or we'll see. To figure out what to do. Okay, let's see. Hello, everyone. Or hello. Okay, let's see. I guess are we lacking who's so Atlanta's not coming, so maybe we're ready. Set. All right.
no. I mean,
Okay.
I've seen him on the weekend, but not recently.
Hopefully not buried in the snow. Yeah. Fighting out. Okay. I thought I would start with there was a nice comment made by Gia online at the end of the last lecture that we have established this basic exponential decay result, and we assumed only bounds on the resolvent from the space X to itself. And we did not assume as usual that even that things were in the just starting. There was made the comment at the end of the last class that in our basic exponential decay result, kind of curiously, we only assumed bounds on the resolvent from the space X to itself, which is not enough to be in the resolvent set. And this was all we needed. So that's different from Hille-Yosida theorem or usual things. Okay, so why? Well, first of all, we assumed an existence and uniqueness in continuous dependence theory, which implies resolvent bounds by Hille-Yosida, but okay, so it's really hidden in there, I think, in the existence theory. But also, it's worth noting how do we get from an X to X bound to an X to D of L bound, right? So here I've written the resolvent equation, lambda minus L U equals F. And then, so U is L minus lambda inverse F. Okay, suppose we have this bound, and suppose we know that just for a single other point, we know that this is bounded. So so the resolvent set is not empty. So I just point out that we can write the equation as lambda naught minus L U equals lambda naught minus lambda U plus F. We can write it like this. Okay, and so now if we happen to know already that U is bounded, well, these are just numbers. So the right-hand side will now be bounded by a constant times F. But this constant could be as large as the difference in lambdas. Okay, but then we've assumed that this is invertible from X to D of L, and therefore we get the bound for all lambda. It's just we don't have any control on the size, which makes sense from the explicit examples we saw of inverse Laplace transforms and how they work.
At the end, you don't need to assume that it is bounded to one value of lambda.
Yes, although we don't even actually we didn't even do that. Let's see. No, we didn't do that. It was subsumed in just assuming this existence and uniqueness, and then that came in various places. That, for example, that allows continuity arguments already because you have continuous dependence and the dense the domain densely defined, so one can take limits to obtain bounds. All these things, they normally would come from closedness, and then closedness would come from a non-empty resolvent set, perhaps. But okay, so maybe that gives a more perspective on this point. I thought it was an interesting point. Made me think about it a little. Okay, so today I'm happy because this is kind of a conclusion of a little part. We've been working hard to set this up. So we now finally have linearized decay estimates, and so I'm actually just beginning. So today we're going to get some conclusions. So we have the linearized exponential decay, and we're now going to use that to get nonlinear results. Okay, looks like we have a big problem, right? Because we lose lots of derivatives in our exponential decay bound. So what we have, assuming good spectrum, where did I use?
Exponentially, as I thought it.
Oh, you mean in X or?
Index.
I didn't use it. No. We will use it though. But after this, we're doing a little module right now where we just look at it like an ODE. We don't see any spatial dependence. But we will have to in the end. Yeah. But that we'll go into a further level of detail. So right now it's not really a PDE. This is ODE in a Hilbert space. But so what we have is that e to the we're looking at e to the LT e naught, and this in the d of L. Sorry, in the X norm is less than or equal to v naught in the d of L squared norm. So that's not with the constant. Oh, sorry. Forgot the exponential decay. So that's H4 if this is L2. So that's losing 4 derivatives. Doesn't look good. But it turns out there's a very nice way out of this. And there's another problem too that we'll see after that. So this is, what is my assumption on the spectrum? I'll just draw it. We're assuming there's a spectral gap.
norm in the right side is the domain of S squared.
Domain of L squared, yeah. Because we had to give up some derivatives to make certain integrals converge by using resolvent identities, and each step we lost a factor of L, and so we lost derivatives. Okay, so here's how we're going to get out of this. Yeah, so it should look like this. Okay, and we're going to see that, well, it's not going to, so first we have to repair these derivatives, but next we'll have to repair something about this, because for traveling waves, it turns out there's always some point spectrum just here. But let me postpone that. So first, let's just prove a general purpose theorem, and for that, we need some repair, and we'll do this by a nonlinear damping estimate. That's what I like to call it. Okay, so now I'm going to write down the equation for the perturbation. Let's see, plus dx squared v. Okay, and then there's a nonlinearity that we up to now have suppressed, but we need to put it back at this point. Okay, so we are going to do, so earlier we showed how you can get resolvent estimates by energy estimates. So we're going to do a similar thing, but we're going to go up to higher derivatives. So let me differentiate. So I get the same equation, essentially. And now I'll take the inner product with the derivative. Okay, so standard energy estimate, the easiest kind. And what I get is, sorry, the time derivative of v of dxv squared over 2, which will be dxv against the time derivative of dxv. And now I have a number of terms. Okay, so let's start with a good one that I like. I've got dxv against dx squared dxv. And this one will be negative dx squared v squared. So that's my good term. I have a number of sort of bad terms, but not really. I have dxv against, okay, so for example, what do I have? I have dx squared a bar v, and I have dx v against dx n of v. And all of these are going to be lower derivatives than this one. So those are order of dx squared v. There will be some of those, but times, oh, sorry, I just write it like this. V h 2 times v h1. Even including this. Okay, so now I can use, as I did before, I can use a Sobolev interpolation. So this will be my good term. I'll take half of that, and I'll use it to dominate anything of size dx, h1, dominate the h1 norm, and I'll get negative dxv squared times a constant. So this goes here, plus a big constant times v L2 squared. after I sort everything out, I can control everything by interpolating between higher and lower norms. So I'll put all the weight on the L2, and what's left over will be absorbed by the higher derivative term. So I can get something that it's two derivatives, but since I'm actually throwing away, I took half of it to kill these other terms, and I'm throwing away. I don't even care. I'm giving up a lot. And I'm doing that strategically because for other problems, so strict parabolicity is really nice, but it doesn't hold in gas dynamics and it doesn't hold in relaxation systems. And what you get out of those, for those kind of systems, this is a damping estimate. It's not a smoothing. I'm just saying that I control the time derivative of that should have been a dx there, of dxv by dxv itself. So it's an exponential, what it is it's exponential slaving of this term to the L2 norm.
The one derivative.
Well, I don't lose it, I'm just throwing it away. I don't need it. I don't need it, so I just throw it away. I used half of it to kill all terms between L2 and even have some left over at the dxv level, and then I threw away the rest because I don't care. I don't care to have smoothing. I know that in some other cases I won't have smoothing, so I'm doing this in a way that would work in more general situations. I'm trying to emphasize that. And okay, so that's the basic estimate. And let me mention, so for gas dynamics, so there's Matsumura and Nishida, and then there's as explained by Kawashima and Shizuta. And this is like 82 or so. They showed global existence of smooth solutions near a constant solution. So stability and global existence. And this was a crucial aspect. They got an energy estimate like this for gas dynamics, which does not have smoothing on the density equation. Mass is not smooth. You have some viscosity, you have heat conduction, but the first equation has no smoothing. So this is all one could have. And that was really amazing, because if you remember the first lecture, hyperbolic systems like the Euler equation develop singularities in finite time. So that was a really kind of surprising and strong result. It's kind of natural, but also it's not at all clear that would be true. And so that was a great result. That's the first example I know of such an estimate. So they proved just such an estimate like this, but then they used it in a little bit different way. So I'm going to use it now. The way I like to use it is I'm going to use an integrating factor of e to the 2 theta. And what will come out of that is that the v at time t and here I did h1, but actually I could do it for any order. It works just the same, just differentiate further. So I have this is less than or equal to a constant times e to the minus 2 theta t minus t, v at time 0 hs squared, plus the integral from 0 to t of e to the minus 2 theta t minus s, L2 norm of v of s squared ds, while VHS is sufficiently small. I need it to stay small to keep the nonlinear terms I keep writing order of v squared, but it's not always order of v squared unless it's unless at least the soup norm is bounded. And in fact, I really need to just have that term be small. No, as long as on S in 0t. I need it to be small on this, so just up to time t. If I know that it's small, I know that it's a bit smaller, perhaps. It's kind of another bootstrap type estimate.
S, what's S?
Oh, S is just, let's see, V of S here. If V of S is sufficiently small for S up to time t, between 0 and t. No, oh, I'm sorry. Yeah, it's not. That's a good point. I should have used something else there. Yeah, let's how about I'll change this H. No, I use S all the time, so I'll use a tau. I'll use a tau.
Okay.
Yeah, tau. Sorry about that. T minus tau. D tau. Tau. Now I'm happier. And then this will be tau. Yeah, thanks. That was confusing. So, and all I'm doing is let me hide this just for a minute. All I'm doing is I'm taking dt dx to the s v squared over 2 less than or equal to -2 theta dx to the s v sorry, negative theta, which let me get rid of this 2. There, now that's plus big constant times the L2 norm squared. And I'm multiplying both sides. I'm bringing this over to the other side. And I'm just using an integrating factor of e to the this becomes plus. Yeah, I'm integrating, giving an integrating factor. And then I'm integrating from 0 to t. And this is what I get. So that's the whole proof. It's just an integrating factor, just basic ODE, and then I get this proposition. So actually my integrating factor is really e to the 2 theta tau. And then afterward, I'm dividing by e to the minus 2 theta t. Multiplying by e to the minus 2 theta t to get this.
That beats all the HS.
Oh, I used it in the let's see, did I think in this particular one is way far too easy. But this is how it usually looks like in trickier ones, like in the Kawashima type estimate and the Matsumura and Nishihara. I didn't need it here. Yeah. But I'm stating things that yeah, I didn't need it. But I could assume this and it wouldn't hurt any argument. So for more complicated cases, maybe I might want that if I want to duplicate this. It's okay. I can still allow that hypothesis, and it doesn't change the application. So this makes it a little bit yeah, as a theorem, it's weaker, but as a method, it's stronger if I know that I can put more assumptions and still works. If that makes sense. Okay. Okay, so everybody okay this with our proposition at this point? This is actually it's like a second bootstrap. We already have one bootstrap type estimate, and now we have another one. So whoops, we're gonna put them together. Okay, so here's my proposition. which is the bootstrap or continuous induction, I will say under our spectral assumptions, that gave exponential decay. We have, okay, sorry, I need to define something first. I'll define alpha of t, as usual, to be the supremum for 0 less than or equal to s less than or equal to t of e to the theta s v h s. Okay, I've got to switch over to tau, as you're right. Tau. There. Theta tau. Then I claim that alpha of t will be less than or equal to a constant times v naught hs norm plus alpha of t squared. So exactly the same statement as we used in previous, as we used for the ODE case, right? For our basic decay estimates. Okay, so now let's prove that. So first estimate, I'm going to do the L2. Okay, so I have V of t is, I'll just use the variation of constants. It's e to the LT V naught plus integral from 0 to t of e to the L v minus tau dx n of v of tau d tau. And I'm just going to use, by our decay estimate, this gives, let's see, actually, I'm not going to work in L2. I'm going to work in H2. I claim so that everything looks nice. So that's actually my base space. Sorry. I've started in L2. Let me stay in L2. That works for I've got an existence uniqueness theory in L2 for the heat equation. So that's fine. Sorry, for a parabolic equation. Okay, so this is less than or equal to e to the minus theta t. Okay, v naught in the domain of L squared, which would be H4. So that's fine. And then I have plus a big constant times the integral of e to the minus theta t minus tau. And then here, what do I have? Well, I lost another derivative. So I'm going from, I guess, H5 of order of v squared at tau d tau. But now I use my assumption. So this is less than or equal to, oh, there was a c here. Sorry, there's always a constant. So there's a big C times e to the minus theta t times v naught h4
Multiplied by the exponential, what
minus theta. Yeah, that's our, this one is order of v squared in H5. It's now 5. That's a 5, not an S. Okay, so now I pull out the e to the minus theta t, and I've got e to the minus e to the plus theta tau. But now here I have pulling out an alpha squared and e to the minus 2 theta tau d tau. because I can bound b squared h5 by, well, all kinds of inequalities, but Moser's inequality says it's L infinity times h5. So h1 times h5 squared is fine. And we take s is bigger than or equal to 5. That's what I need. Forgot to write that. This is bounded. This is integral. So from this, applying now to tau, e to the theta tau, v of tau, L, put it outside. L2 is bounded by a big constant times v naught h4 plus alpha of t squared. Any t greater than or equal to tau. Because to apply the alpha of t, I need t to be bigger than tau. That's the definition. Yes, where is it? Up at the top. I need t bigger than or equal to tau. That's fine. But now I'm done. I'm done for L2. Only for L2. I lost a lot of derivatives, but that was enough to get the L2 bound. Okay, but now this part is kind of fun. Now we go to straight to HS. Now we use the nonlinear damping, and we have E of t hs squared is less than or equal to e to the minus 2 theta t v naught hs plus, okay, the integral e to the t minus theta t minus tau. What do we have? Dx. I'm sorry, no, we have v of tau L2 squared d tau. And now we use the fact that we've already bounded this. And this is bounded by less than for tau less than or equal to t, as it is in this integral. This is less than or equal to a big constant times v naught hs plus alpha of t squared e to the minus theta, 2 theta tau. Okay, so t here, there's a tau that goes there. This is what we just proved, a bound for L2. But now we're in good shape because this will be a big constant, e to the minus 2 theta t times v naught hs, okay, plus, okay, so I pulled out the theta t, oh, this is 2 theta t. So here I have integral of e to the 2 theta tau let's see. That was, I've got the square, sorry. Here. That's squared. This is squared. And I've got exactly what I don't quite want. Apparently got something canceling. Let's see. Where
In the integral, would that be order of fourth rather than order of two because you do square on both sides? The L2 norm fourth order.
well, I proved, what did I prove here? Well, my assumption was just e to the theta t was the bound that I proved, e to the minus theta t for L2, so I get e to the minus 2 theta t. I think the answer is that what I have to do is I have to use the fact that I could have put, by relaxing my linear decay bound, let's see, or sorry, relaxing my my theta a bit. This one used the exponential decay bound. I actually need to I need to take this theta slightly bigger than the other theta. This is what I need to do. Sorry about that. I need to take this, I need to have a theta tilde, and I need theta tilde less than theta. I need to use a weaker estimate, and I need to, let's see, is that going to work out? Yeah, and it's not quite going to work out. Something's bothering me here. Okay, I'm gonna have to, this is, I don't know what I did.
Kevin,
Yeah,
Kevin, I
you
think
help me out?
I think the integral would that be the L4, the fourth order because it's nonlinear term, right? So it should be higher order compared to other terms. So
We
the
have that here. Yes, we have that here. Oh, thank you. Yes. You're right. I've got yes, I've got extra decay there. No, I used that. I did use that here.
you didn't use it on the right board, the latest board that you didn't. Because you put it, the left hand side is HS square, so right hand side should be fourth. Yeah.
This should be V0 squared. That's
This
true.
is square, and inside the integral is fourth
The fourth.
because it's nonlinear and square. Or it's nonlinear square, so it will be smaller.
Let's see. What I'm using this one is my problem. This one, which is.
But even in this proposition, it should still be something square, right? Because the only thing that you get from the error is square or something.
Yeah, it is squared, and then.
If I understand well,
Yeah,
in that estimate,
Yeah.
you included a part of the linear operator
Yes, I did.
in the fourth term.
I did, yes.
That's the
So it's only squared.
Yeah, so it's squared.
Yeah.
Yeah, I see.
This V of L2 without square. And V of L2 without square involves the non-linear term, which down with a square.
But this is how I got the alpha squared, though. That's how I got the alpha squared in there.
That's correct. This is correct.
But I think this is all I get. Think I got a cube here? Okay. Let's see. I multiply by dx s of v, and then I have, but I had some linear terms in there, which I subsumed into L2 squared. I don't think for the nonlinear term, it becomes cubed. Yeah, that's true. But this included also linear terms in this estimate here. So I'm a little bit yeah. I'm going to just repair this next time. I just wasn't keeping my eye on this close enough, but I'm not sure exactly what it is, but okay, to be repaired. Sorry about that. Speaking of repairing. All right. But the idea is that this should then converge. And so using that, square root of a plus a, let's see, what do I have here? I've got a squared plus b squared, and I can bound that by a plus b. So I can just remove the squares basically and add everything up, and I get just v naught hs, and then I get, well, which should have been squared here, and then I get alpha t squared. So I get, I'm going to get the bound that I want. I'm going to get that so long as that integral would converge, I would get hs times e to the theta t would be less than or equal to a big constant times v naught hs plus alpha t squared. That's what I want. And then I would be done. But I didn't set it up quite right, or at least I don't see that I did, to make the integral converge. You see that? Yes. Yeah, we could do it without L2 if that helps, but let's see. Okay. Yeah, sorry about that. Okay, so we'll come back to this. But of course, once you have this bootstrap, it's the same argument now. Immediate corollary is the nonlinear stability with exponential decay rate. Of course. Okay, so this part's fine.
Maybe the growth is slightly slower than theta, the alpha t when you define. Would that be?
Well, I think I need to play with the two thetas, which is typical in these contraction mapping.
Yeah, because the linear give you the e to the negative theta decay, and from the energy estimate, basically you get a boundness upper bound. So if you want to get HS, it's kind of some interpolation between them. So should be loose a little bit, I guess.
I think that's what's going on. Yeah, I think I have. Yeah, in both of them, I can play. Let's see. Yeah, I can play with them. I can, of course, I have a certain amount of linearized exponential decay. I can give up some. It's still true. But also here in this bound, but the way that I did things, I could have made that constant as big as I like. I could have made the theta in the damping. I can make that as big as I like because of the way that I estimated, but because of this interpolation, I would just have a bigger constant c, which wouldn't bother me. But so I'm going to play with that, and I'll come back with a fix. But I'll just say that, state the corollary, which is under our spectral assumptions, we have for V naught H5 sufficiently small, global existence in time with exponential decay in H5. And so that's exactly what we had for just ODE, and that's great. It all comes back fine.
Yeah, thank you.
But of course, you need to have solid proof along the way. So we'll fix that. Okay, but Okay, so that's one sort of goal achieved, just to equal the Lyapunov theorem for ODE. Yes. You had just looking. Hmm. Okay. But of course, we're not done. This just says, it says if you have good information about the spectrum, which is still a bit murky, it's not very concrete for ODE. It's a linear algebraic calculation. We don't know where or what really the spectrum is yet. We're going to have to investigate that. But also, we've assumed a spectral gap. And that one, at least, I can show you it's not true for traveling waves. It's never true. Okay, so that's a first issue. So we have still to do, we have verification and investigation of the spectrum. And then we have, so that's one point, but we also have that traveling waves have a zero eigenvalue. Which is only neutral. And this is always true. And the reason for this is, and it's sometimes called a translational eigenvalue. And the fact is, if W bar of X is a standing wave, then W bar of X plus delta, which we'll just call W bar delta of X, is 2. Because the background PDE was independent of X. Okay, and therefore, delta perturbation, so W bar of X plus delta minus W bar of X, this is a standing perturbation. It never goes away. It just stays constant under the evolution. So at the linearized level, so if we take d by d delta of W bar delta, which is the spatial derivative of W bar by inspection, if we take this at delta equals 0, this is this satisfies the variational or sometimes also called linearized equations. It's a stationary solution of the linearized equations. Just by the fact that when you linearize, that's just one kind of variation. That's a variation in V. You could also take variations of other sorts. So this one, there's a symmetry in the equations. We're taking a variation along that symmetry. And so it logically follows that this will give a stationary mode. But let's just explicitly calculate it. Okay, so we have the standing wave ODE is A bar W bar dx equals dx squared W bar. Let's take another derivative. So that gives dx of, I'm sorry, I should have written it. It's dx of f of W bar. And I want to notice that that is equal to, that is K bar dx W bar. That's another way of writing that. If I take a further derivative, I get dx of a bar applied to dx w bar is equal to dx squared of dx w bar. So taking this as v, taking this as our perturbation, we see it exactly satisfies the linear equations with zero time derivative. So this is a stationary solution of the linearized equations or zero eigenfunction, because this says L dx w bar equals 0. So that's always the case for any traveling or standing wave. And it means the spectrum does not look like the good picture, but at best, okay, at best it's going to have a spectral gap for all the remaining spectra, but it will always have a zero eigenvalue. Okay, so if I timed this right, which I kind of did, I think let us stop there.
Essentially, the theory doesn't apply.
The theory does not apply, and yet there's a very nice argument by which we can recover the theory. And basically the idea is, well, why is this here? It's here because of a symmetry. Well, there are some nice approaches, this idea of equivariant stability that somehow, the answer is that you need to quotient out the symmetry and then understand it in the old way. So I'm going to do an argument like that, but phrased maybe slightly, no, it's really phrased pretty much like that. But okay, so that's what we'll do. Let's take a break here and start on that after. Okay, so a 5-minute break roughly.
Ça c'est donc la bonne hypothèse spectre. Il est un jeu spectre. Et je suis curieux, et je pense que c'est ça où on va utiliser l'exponentielle.
Oui, je sais pas. Parce que L, chez L, c'est A, c'est dx, A de x, c'est
divergence.
A vers c'est
Oui.
C'est une matrice rationnelle. Et ouais, la pression de moins dx tout ça.
Moins dx carré plus un potentiel plus un transport. Non, parce que c'est sous forme de divergence. C'est moins dx à dx carré plus divergence de A bar dx. A bar dx de A bar et dx de A bar. Il y a un transport et un potentiel.
C'est comme ça, non?
Ouais.
Ah oui. Il n'a pas exprimé comme ça.
Non,
Il va
voilà.
le voir.
Mais voilà, effectivement, lorsqu'il va étudier le spectre, c'est ça, c'est.
Mais il faut la linéariser par rapport à la linéarité.
Donc c'est ça son.
Ça, c'est elle.
Voilà, ça c'est elle. Ça c'est elle. C'est
But somewhere, Kevin, we will see the linearization near the shock of your traveling wave, which is like this.
Yeah, yeah. This comes next. We're setting up the,
Yeah,
but it's coming very soon.
I expect like this exponential asymptotic would be useful there.
Oh, it's very, it's crucial.
But it's a brilliant idea. I mean, I kind of feel it's like 2 years ago. We didn't know about it, but it's very important.
Yeah, the exponential.
Yeah.
Yes. So in what context did you encounter that?
Actually, our master student, he discovered that. Yeah. So he was basically studying something away from. Yeah. So he, I mean, he was reading. Yeah, I mean, it was the first time I experienced that. It's actually heat technique.
Yes, this is all, that's the.
It's all yeah, very nice, very nice. I mean, I've never seen that.
The one I'm gonna show, so right now I'm gonna do the equivariance, but just after that, then I'm gonna do this ODE thing that you're mentioning. To me, it's like a Fouquet, the Fouquet, that says if you have periodic coefficient problem, you transform it to constant coefficient with a periodic coefficient equation. This says if you have exponentially asymptotic constant, you transform it to constant coefficient.
Yeah.
With an exponentially.
Yeah. It's amazing. It's amazing. Yeah, it's amazing. Yeah.
And it's just as useful, right?
Yeah. I mean, when I see the first time I've seen that, I mean, I was well, what did you get this? I mean, I never heard about it, but
yeah,
I think that's very. So I didn't know that you use it, but now I know. So this is great.
yeah, oh yeah, definitely. That is the cornerstone to some stuff, but it looks like.
They're all the same.
They all do. Yeah, right. That's that. Even before we had kind of a lesser result that says here every constant coefficient mode, again, every decay mode, there would be another, or there would be a variable coefficient one that's asymptotically lengthened. But even that, you become so confused when there are parameters in the problem. Like the frequency, that it's always there.
Yeah.
Sometimes there's a Fourier mode if you have diminishes, and it quickly gets more. And so knowing that you can just make it constant coefficient makes so much better.
Yeah, of course.
Now it's linear out.
Yeah.
You can do it.
Yeah.
Or if you can't, then there's no hope.
So what was really the most important point was the character of the spectrum. I mean, forgetting about the lambda equals 0 because it's due to the form of the description of the spectrum.
It's gonna be really important. And to get the description of the spectrum, we're gonna have to use this conjugation to constant coefficients. But that would also tell us the resolvent. We'll know the spectrum by knowing the resolvent, because that's how we do it. So then we'll have resolvent estimates. Sure. The tools.
But the second traveling wave is important here, or it's
Very important.
whether you use it.
I think it is exponential. I think.
It's not, yeah, so
Not
far,
here,
this
not
is
here,
the.
not here. Yeah, because I mean, his profile or traveling wave is constant. Constant minus infinity, yeah.
Nothing.
And then he will focus on the maybe the music, I guess.
Yeah, you see, but basically, here we suppressed all that because we just said it's the spectrum is good, it's good.
Yeah.
But how do you find the spectrum?
Yeah.
It comes from the shape of the travel.
That's-
Yeah, this is the expression.
Because in other problems, I mean, the one that we are more familiar discussing problem is always the shape, I mean, the character of the spectrum, linearized, give you Oh my God.
So, but you, is that beyond, well, so it's running on something like mouse states, that's what. Wait, sorry. And obviously that comes out of the potential on the shoe. But also you could have, so when you're talking about normal modes, I think you mean essentials.
Just modes that, for example, response to purely imaginary.
Yes.
That
That
we
change
did-
expands.
And then we decay. It's a bit of a long time.
So like you say, dispersing estimates. Coming stationary.
So you would have, so it can be, I mean, we would have three components essentially, very fast dispersal. The solitary wave and decay. Sometimes. Then you would have this extra solution that decays so still disappear. Wait. So it's a little bit different kind of level to keep. Still, the spectrum.
It's the most challenging thing.
The half.
Yeah. That's why I'm awake.
Oh, yeah, when we're going till 5, probably it should be stopped.
I was just thinking before Kevin's lecture, so I can.
Yeah, I just followed Yaka, I followed suit with Yaka. Yeah, 1 hour and then 1 hour,
Yeah.
so I just reversed it so that they was. Yeah,
Oh, he does 2 hours, 1 hour today.
and then 2 hours. No, actually, I think he might be Monday and Wednesday.
Tuesday. Yes, yes, yes. Yeah, Monday, Tuesday.
So it actually doesn't interfere, but there was some other class that I would have interfered with.
And at the end, the 50 students are on the screen.
Oh, really?
Just every day.
But from this. But maybe if you know from the other class, I don't know.
Well, for the other ones,
Yeah, complaints.
probably it was making us feel that was it the cost, right?
Which
That will be a geographic relativity.
okay. And probably there are also more people working on that because there's Stefanos, Spiros, a lot of people in GR. Yeah, also, yeah. So they that's a yeah. Like, oh, fun. Yeah. So, you're right.
I think I can. Do something.
And maybe they are going to start with. No, but. Ich bitte mal jetzt. Das wird noch jetzt mal. David, do you know if they're going to open types for substance now?
Like in general, like most of
Here, yeah, but like a weekly seminar, or you don't know? So maybe it's a order.
yeah.
It's the cost of people. It's Alan. But
Yeah, no, absolutely.
Okay. Okay, so I'm going to talk about ectoperic decay methods, results, and this is related to the freezing method of fine. It's a nice way of thinking about it and discussing it. And some other versions of this, Goodman, Ashiadai. Okay, so there are some many versions of this, but I like. I do this is most closely. What I'm doing here is most closely connected to minds. Work, and I learned about that. It's kind of idea for Jonathan Goodman. Yeah. The other person is Corrado Masia, who he and I wrote a paper on stability of relaxation shocks.
But before buying.
Yeah, it's actually before, but it's specialized to our setting.
Okay.
But it was a little different. So what I'm showing here is kind of big. He had a wider perspective, very, very broad. Think of symmetries in general. Not knowing. It's used on many interesting problems for bifurcation and so on. But I've only recently learned about this. Very nice. Okay, so. All right, so the idea is you introduce sort of pull back variation. So you don't want to vary around a moving wave. You think this wave's going to move around as things go, but you don't want to linearize around a moving thing. You want to linearize around one thing. So what you do is you translate the curved solution and you subtract off fixed one. So this is the same another shift as subtracting W bar of X minus delta from W. But it's more favorable for analysis because we can linearize it. So better always stay fixed as close as we can. Stationary. Okay, so now we get so delta is the phase, a phase shift. Simply. And okay, so what does the equation look like? We easily find that TB minus L around W bar. The usual same L as before, but I'm emphasizing here. Is equal to dx n of v. Same definition as before, but now we have a couple more terms. Okay, so spatial derivatives of v, they work just the same. Basically, we subtracted derivatives of perturbation from some subtracted derivatives of the bar from derivatives of perturbation, and then we got derivatives of v. Well, that still happens with x, but when we take a time derivative, it brings in some extra x derivatives. And so what we'll get here is minus delta dot of t times w bar plus v with the dx. So that's our new equation. Just had this confirmed. Okay. Now we're going to assume spectra of the bell that draw a picture. I'm going to assume a simple zero eigenvalue. So only symmetry is responsible for the zero eigenvalues. No other zero eigenvalue.
When you have the double of X vector T and comma T. Because the double depends also on variable T in the.
Ah, yes, sure. Yes, I mean,
It is just to make sure that.
yeah, but that's. That, yeah, yes. Now, let's get into. Relations, not much. There's only the time derivative that they changes. So we're gonna assume that the rest of the spectrum it has a spectrogram. And here I'm, by this I just mean the rest of the operator, you know, the projectile, take out the.
So the existence of W bar is an assumption or it's always
Yeah, I'm assuming there's a traveling wave, so. Yes,
so a steady
steady, W bar,
station.
standing waves.
Yes,
I'm still not using anything about structure of the standing wave. Because I'm just making assumptions about its spectra. To verify those, I will need to know about the structure of the curve. But if I just assume these things,
Sorry, this is the real part of the spectrum of.
this is an L tilde, and this is the rest.
What is
the rest equals L minus projector onto 0.
Okay.
Could W be a constant?
What could be a constant? Yes, it could be constant. So, and all this is still a whole. Yeah, and actually, that's often a good thing to think about. Because constant solutions, we can study their linearized equations using Fourier transform almost exclusively. A very good exercise is then try to recover those things by Laplace transform. You see that the change is not always that trivial. Of course, they're equivalent. There's a one-to-one correspondence that doesn't matter. But if you put aside your Fourier calculations and just try to start from Laplace, sometimes it looks bad.
Expected when you say this, the real part, I mean, the real part of the symbolic and values.
No, the real part of the rest, is this is L tilde defined to be L minus the stationary projection. And the stationary projection is the residue and lambda equals 0 of the resultant. And that is equal to R, their product of L. And R is where L and R are eigenvalues. R and L are right and left. 0 eigenvalues. By the way, I know what R looks like. R is EX W bar. That I know. Because I assume there's a simple eigenvalue, a 0 eigenvalue. I know this is an eigenvector. So it's simple, this is the only one, just multiples. Now, loss of generality, I can take it exactly EX W bar, I'll rescale L accordingly. And we have L dot R, L inner product R equals 1, the usual. It looks exactly like finite dimensions, but is this the L2? That's what. So that's our assumption. And then our conclusion is going to be
Professor Zumbrun,
it's
is your microphone off?
yes.
Okay.
I don't know how that happened. Yeah, maybe at the break. I thought I checked it. Thank you. Is that better?
Yeah.
Okay. Sorry about that. Should I restate the theorem? Yeah, maybe. Yeah, I will. Okay, so you followed the definition of the perturbation?
Yeah, I
Did
mean
you?
we could mostly hear most of what you said.
Okay.
Yeah,
Well,
it's
so
almost
if we
clear.
define
Yeah.
this sort of sliding perturbation with phase shift delta, then by direct calculation, the nonlinear equations, they look the same as before, but with this new term involving the phase shift. Now I'm going to state a theorem. The equivariant stability theorem says we make spectral assumptions that this translational eigenvalue, which is always there, is the only zero eigenvalue. It's simple. And the rest of the spectrum has a spectral gap. It has real part strictly negative. And I'm introducing this operator L tilde, which is the complementary operator to L. So it's L minus this projector onto 0. And okay, that's it.
Is that what's L? Small L?
Little l is a left eigenfunction. So it's a zero eigenfunction on the left. And we know that this exists. How? By Kato's theory that we didn't really do. But the residue, we know that the projector is the residue of the resolvent. And by further examination, one finds it must be of the form expected. But I didn't do that part. So I'm just asking you to take that for granted, but that comes out of the theory. And actually, we'll see this. We're going to do some explicit computations that show this structure very clearly in a couple of lectures. So you don't need the background Kato theory. We're going to compute this. We'll see it. What the resolvent looks like and what the pole looks like. And so it will have this form. Okay. And then the conclusion is, okay, so the conclusion is, well, it's the one we want. I'll jump forward here. We have, okay, for W minus W bar sufficiently small, there exists a delta of T such that V exists globally. With 1. Okay. W of X plus delta minus W bar of X. So that's actually just V. HS, and this is for S bigger than or equal to 5. I should have said it's up here. S bigger than or equal to 5. Then this is less than or equal to a constant times just wrote this. W minus W naught minus W bar HS e to the minus theta T. Delta dot of T is less than or equal to a constant times W naught minus W bar HS e to the minus theta T. 3, delta has a limit. Delta infinity as T goes to infinity with delta of T minus delta infinity is less than or equal to a constant times the initial perturbation HS norm e to the minus theta T. And last, delta dot, time derivative of delta, is bounded by the same constant. So effectively, the idea is where we're going to kind of factor out this translational symmetry, and then we get, okay, so we get the same bound that we would expect without that zero eigenvalue for V, but V involves a shift. And so we would like to know the shift stays rather small, and that is the next, item. Oh, just a second, what did I do? Oh, no, the last one is, I did two. The last one is delta of zero is order of V of W bar, W naught minus W bar, HS. W at time zero. Sorry, W zero. W zero is the perturbation. So W is a perturbed solution. W zero, that's W of xt. W zero equals W of x zero. And so I want to write it in terms of this because a priori I don't have a delta. There's no delta. I don't know what V naught is until I know what delta of zero is. So I have to figure that out along the way. And okay, so I'm saying there is such a delta that makes all of this happen.
Delta has limit, delta zero.
Yeah, delta infinity, it has a limit as t goes, oh, I wrote zero, as t goes to infinity, yes. And it also has a starting point, which is of the size of the perturbation. In fact, it's the size of the L2 size of perturbation, so it's even easier. Yes. And and also the starting point, well, it has a limit as it goes to infinity, which is of this order, because the difference this says if I put in delta zero, I get yeah, I have a bound on all. Let's see, what do I need to know? Yeah, I need to know, I know that the difference from the final limit is decaying exponentially, but I would also like to know that delta stays small. Otherwise, it's not a nice bounded stability result.
How do you define delta of zero?
This is what I'm saying there is a delta, which I will have to define in the proof. That's delta of zero. This one is delta of zero. So I'm just giving some information about that delta is pretty small initially, and it changes exponentially small.
And sorry, and number two is delta with a dot. It's a derivative of delta.
Yeah, that's the time derivative of delta. That's exponentially decaying. Yeah. Which actually immediately, so this immediately gives this, but it doesn't give this. Then we want that too.
The top of the. So initially, you assume initially it's sufficiently small.
Yes.
That's it.
That's, yeah. Thank you. That's W zero. Yeah. So I'm assuming it starts out sufficiently small. And at this point, I don't know. I don't even have a definition of a delta. There's no, there's no unique definition. No, one could phrase a theorem like that, but it would be a much less satisfactory theorem. You would have to build in a phase, and you don't need to build in a phase. You can figure out a good phase. A sort of a best phase. Yes, this is, so this alone would be orbital stability. Let's see, and these together give phase asymptotic orbital stability, which is Sure, it's sure, actually. Couldn't be. There are many examples that show that, there's, well, okay. You could just take the initial perturbation to be, you could take this to be zero. That would persist, right? So it's delta cannot go necessarily back to zero. That would not be the case. So this is really the best one could hope for. And it is correct.
Is it a unique way to choose delta?
No, I think, yeah, there could be many other ways. Choose delta. And in fact, it will be important for the actual viscous shocks to choose it in a different way, strangely. But when you have exponential decay, a spectral gap, this is optimal. And there's no better way. But in other situations, there could be more strategic ways to do it, strangely. But not when you have, not when this is an isolated, when this is isolated from all the rest, this is the best choice. The choice that I give you is really the best and the most natural, I would say.
Elegance of that, the fact that your notion of orbital stability is hidden in the delta.
Yes, it is. And okay, so yeah, so what I'm going to do next is basically define delta in a nice way. Okay, so let's see. Okay, so basically, so we have e to the LT is e to the L tilde t plus pi 0. Because of the way we define pi 0 is just projection onto the stable mode, the zero eigenvalue. And then these have a spectral gap. And therefore, by the same linearized estimates, but now on a new Hilbert space, which is the complement or new monic space. We didn't use Hilbert space. A new monic space, which is the complementary subspace of the range of pi naught, we get time exponential decay. So e to the L tilde t is less than or equal to a constant e to the minus theta t. So we have a decaying part and a stationary part, and we're trying to separate them. And we also know little l against little l against L tilde is 0. L tilde times anything. Why? By orthogonality of left and right eigenspaces. This annihilates this annihilates the 0 eigenvalue, and this is only responds to the 0 eigenfunction. So we know that. Okay, so what we're going to do. This is sorry. This would be L2, and this would be. Let's write it like this. H5. Same kind of loss of derivatives.
Where this loss of derivative come from?
That came from it came from using the inverse Laplace transform to directly get exponential bounce by moving a contour over into the negative half plane. So we moved, this is where we took our contour. So we took a real part of lambda identically equals gamma, so a vertical line. And so in the Yeah, so we've got e to the LT is the integral of e to the lambda t, resolvent, d lambda. If lambda has a negative real part, there's their time exponential decay, and we just needed that the rest be bounded, be absolutely convergent, but it's not until you use some resolvent identities, which trade decay in lambda for powers of L. And every power of L loses two derivatives. We had to do it twice. And then, so it actually was, I'm sorry, this was from 4. This was H4. We lost another derivative in the nonlinear term, but that has nothing to do with this. But yeah. And
Hi,
obviously we're not.
Are they always orthogonal or
left and right eigenvectors are
oh, they are
orthogonal.
left and right.
Yeah, so if I'm really saying yeah, stick in any v over here, this is identically 0.
Okay.
Because this L tilde the range of L tilde is orthogonal to L.
Yeah, thank you.
Like matrix. Yeah, so I'm not assuming a symmetric operator or anything. This is true in general. And I'll need that. And so basically my idea is I would like to work on the range of L tilde. This is where I would like to be. That's where I have exponential decay. So it's natural, I think, to ask that we arrange that L inner product with V of t is identically 0. And if we do this, we should have, then we think we should have exponential decay. But how can we do this? So this is the idea. It would be nice to stay on the decaying manifold. And we'll see that does work. Let's see. Okay, so. Okay, so step 1. We need at least L V of 0 equals 0. We've got to at least start out on the manifold. And that means choosing a delta. So lemma, there exists delta of 0 equals order of W naught minus W bar in L2 such that L against V of 0 equals 0. Okay, so the proof, I just have to write down what this means. This means equivalently, 0 is equal to the inner product of L against W naught of X plus delta minus W bar of X. And then I'll rewrite that as L against W naught minus W bar at X plus delta plus L against W bar of X plus delta minus W bar of X. See, I hope I did that all right. I think I did. Okay, and this is the thing that, this is our initial perturbation. As is given to us in the problem with no delta. Okay. All right. So it's kind of like known. Let's just call that Z naught. It's just something and small.
And then
This is just where I'm evaluating them both at X plus delta, both terms. But here, it's delta of 0. Oh yeah, delta of 0. Thank you. Delta of 0. Yeah. And then this is delta of 0 as well. And I want to choose a delta of 0 that makes this happen. But I can Taylor expand this as that's delta dx w bar plus order of delta squared. And then okay, let's go over to this board. Just copying things. I want, let me pull this over onto one side. So I have Z naught against Z naught of, sorry, L against Z naught of X plus, no, just Z naught. Z naught fixed should be equal to, okay, so we've got L against dx w bar delta of 0 plus L against order of delta of 0 squared. And this, I know that L dx w bar is 1. That's the normalization. This is a right eigenvector. This is its left eigenvector. That's by definition. So I have delta of 0 plus order of delta of 0 squared. And this is the input. This is known as small by assumption. It could be 0. It could be 0. Z naught could be 0. In which case, yeah, right. But so, and here I'm using already. I'm using that L and R, which is dx w bar, are in L2. In fact, in fact, they're in H4. Because I used I used Cauchy-Schwarz here to say that this was order of Z naught H4, which was assumed small, because I know that this has a bounded. It's just I'm just working it. I just need L2, just L2. Okay, so this is a contraction mapping argument. Or an implicit function theorem, and it gives a solution. I think I lost that. I think this should be a negative over here. But anyway. Or this, no. It's just that there exists one. Okay, so that's step 1. And then step 2 is we want to make sure we stay on the manifold. So now we have to look at the derivative. Okay, so now we need dt of L v of t identically equals to 0. And this is L against dt v. And recall what dt v is. There it is. dt v is L v plus dx of n of v minus delta dot of t v plus w bar. So we want that L should annihilate all of this, little l. But first observation, so taking L against dtv is L against LV, which is 0. By assumption, we're assuming that we're on the by L V of t equals 0 assumption. If we're on the complementary subspace that's preserved by L, this will still be 0. So it's the other ones we need to worry about. And those are L against dx of n of v minus delta dot v, and then plus L against delta dot dx w bar. Okay. Minus delta dot of t, sorry, of t times v. So this is just now a new kind of a nonlinear term in there. With instead of order v squared, it's order delta dot v. And then we've got this other one out here. And okay, this one, so this one disappeared. That's nice. We want all of this to be 0. We want it to vanish. And this one is really nice because L against dx w bar is 1. So this is, it's very much like in the previous scenario. This is delta of t. So we want to set delta of t to be the negative of all the rest of the terms. So we want delta dot of t is equal to negative L against dx n of v minus delta dot. Well, let's just put it like this. No, that's what I want, delta dot of t. E. Sorry, no, I still want to split this. Okay, this is what I want to do. And it looks implicit, but it isn't really, because I can just divide by this term.
It's a bit like what people call modulation.
Yeah.
When they modulate your parameter.
Yeah, this is a very simple modulation though, because there's only the one parameter and it stays fixed in space. It's only depending on time. This is a really simple modulation. Yeah.
More like parameters that depend on time.
Yeah, but I'm thinking also in X, often they depend in, like for periodic, like your I'm thinking of some of your works actually on the water waves and the flux spectrum and things. Yeah, then it would depend on X, but here it doesn't. But I'm going to rewrite. I'm going to solve as, okay, so delta dot of t will be, okay, 1 minus L dxv. On the denominator, on the top, it's L dx n of v. But I'm going to go one step further because I can integrate these by parts. So that's L sub x against n of v over 1 minus L sub x against v. Okay, and something that's not obvious at this point is, but we knew that dxw bar decays exponentially because the traveling wave does. But we're going to find by a study of the resolvent equations and the eigenvalue equations, we're going to find that that's actually true of the left eigenfunction as well. It also is going to decay in several derivatives, but I'm going to postpone that till later. But definitely, we'll see that. So L and dx w bar decay exponentially in several derivatives. So that's to be paid back pretty soon, within a lecture or two. But for now, we'll just assume that. So this is order of the L2 norm of V by Cauchy-Schwarz, because this will be in L2. So they're in all L1 intersect L infinity. I can bound either of these by whatever norm I like that's convenient. And the convenient one here would be bound this by L2. So this inner product would be bounded by L2 norm of V times some constant L2 norm of L sub x. And V is assumed small, so it works. Yeah. And what I will get is right. Yes. And then this one, let's see, I guess I have a V squared. This is order of V squared. So I think I'll want to take the L1 norm here and the L infinity norm here.
Just about the sign,
Did I, oh, I think I did the sign.
So in the
So this should be plus? You know, it's
no, that's the second. So you integrate by parts.
Okay, good. Yeah. Oh, but then this one's okay too, huh? Because they're both okay by integration, because I integrated by parts. I'm saved. Yeah, it was right. Sorry about that. Yeah, that wasn't well done. Okay, so yeah. So this is order of, so the top is order of L2 norm squared, actually. Isn't it? No. Just L2 norm. Just L2 norm. Yeah, because I'm pulling out. No, it's the L2 norm squared. Yeah, which is still small. That's fine. And this one has an order of V L2. So yeah. But yeah, this is L2 squared. If I take the L1 norm of this, that's the L2 norm squared. Yeah, so it's quite small. Yeah. Okay, so it's looking more and more harmless. I thought it was order V perhaps, but it's order V squared. So it's small all by itself. But notice it also, yeah, okay, so I can do it. And not only that, I've removed delta dot. It's now, I can now treat it as it's a function of V. So I can study the V equation all by itself. So now let's go and write down the solution. Using variation of constants. V of t will be e to the LT V naught plus integral 0 to t e to the L t minus s, or t minus tau, I guess we've decided on, and then dx of n of v minus delta dot w bar plus v of tau d tau. But now I've split this into e to the L tilde t V naught plus integral from 0 to t e to the L tilde, the time decaying part, the time exponentially decaying part. Okay, and then we've got n plus delta dot W bar plus delta dot V. That's tau d tau. And one thing I notice is that here, this term is actually equal to, with its dx of W bar times delta dot of t. That is annihilated by the L tilde operator. This term is not there. That's important for us. We don't want that term there. And the rest is dx W bar. So it's this projection onto the zero eigenmode, basically, of so it's L V of 0 plus integral from 0 to t of L against all the rest, dx n plus delta dot v of tau d tau. This is what we forced to be 0. This was step 1. We arranged that this would be 0. Initially, we would be on I'm splitting L into, so e to the L t of v is equal to e to the L tilde of v t v plus L v dx W bar, which is a stationary. So I have the time decaying part, and then I have the stationary part. So I'm just splitting it like this. And in the first line, I put group the L tilde terms, and I noticed that one crucial one is not there. The one with so all the dx W bars appear in the second line, which is just dx W bar times inner products with L. Does that make sense? What did I leave off? Oh, when I remove this one, I removed this one because I know that this is the 0 eigenfunction. It's killed by L tilde. And then down below, yeah. So this is now this is getting very close to our idea that we just want to, work only on the L tilde space. Well, we have managed to do that, but to do so, we had to define delta dot in this way. So we actually have, this is one of the equations. So we've changed it into a system in V, but it's not really just any old V. You could call it V tilde. It's the component of V in the good, well, it lives in the good space, the decaying subspace. And so we gave up one parameter. That parameter that we gave up now appears here in a very explicit way. Okay, and then this term, though, this is order of VL2 squared already times another V. It's better than n of V. So so this is all gone. This is by step 2. That's exactly what we manufactured delta to kill. And therefore we are left with just the first line. So the cheat, because we're at the end here. Right. And this has exponential decay if we can prove a nonlinear damping estimate, because we have to still gain back derivatives. And that I'm going to do next time because we're nearly out of time. But the nonlinear equation is now slightly different. So we have to, make sure the energy estimate works. But it will. So we're going to stop here with let's see, what do we have? We have okay, we have a nice exponential bound. We have part of a bootstrap bound. We just basically have these equations. So we've got a nice subdivision. We've got a very favorable looking equation. We've got in V alone, we've got a harmless slaved equation, delta dot. So it's just of the order of the L2 norm of V. If V is exponentially decaying, this will be 2. So that part's going to be very easy. And really all we need is to gain back our derivatives and do a damping estimate. And I'll do that next time. That also turns out very nicely. So
choosing your delta, you were able to go and the first step and your initial delta also, you were able to eliminate the zero mode.
yes, that's the idea. You just eliminate it altogether.
Are left with the L
Yes.
in the estimate.
And that one is decaying. Yeah. Yes. They live in H4, remember. This we know just from, right, the resolvent goes from L2 to H4. Sorry, the resolvent. And we're taking a pole of the resolvent. So its range is in H4. And these are by definition in the range of that operator. So we know they're H4. What we don't really know, and let's see. So I used somewhere that it was in L1 instead of L2. But we'll see that that's okay. I could I don't know what to do if I don't have that really. Then I have a little trouble because now where did I use that? Right here. Let's see. Now this one was. I could probably get around it, right? But I could just Sobolev out one of these guys. Yeah, I could mount it I could pull out an H1 norm of V times L2 norm of V. I guess I'm okay with this just being in L2. Yeah, I could have done it a different way.
Little N equals to R,
Actually, for viscous shock waves, it turns out you do. It's 1. Basically, it's a constant because of conservation principles. But in general, no. If it were self-adjoint, yes, we know it's dx w bar again. And kind of the opposite case would be the shockwave case. And there we know it by conservation. But in general, we wouldn't know what it is. It doesn't matter for this proof. Yeah, no, it doesn't matter for much, I guess.
Hi, Kevin. If you have the not single eigenvalue, but would that prove the same?
Well, it depends. If your eigenvalue comes from other symmetries, like maybe a rotational symmetry you might be thinking of, thinking of your recent lectures, that would be okay. You can have multiple parameters, and it works out well. It's a little trickier to write down. The equations are trickier to write down because I took advantage that I could just put this phase in as an additive term in the independent variable. But then if you have rotation or something like this, you have to write it in more geometric form.
Yeah.
Yeah, like you have to introduce a symmetry operator and but yeah, but this is done, for example, in the work I referred to of Vine.
Okay.
You can find rotational. I think it's largely about rotating waves. Some of the early papers. So you could find there a different exposition.
Yeah. Thanks. So when would it may depend on X? So here it only depends on T. So when would it be
Oh, when
more
would it depend on X?
Yeah.
When you study periodic patterns, you need to allow it to depend on X, it
Okay.
turns out. It's not, yeah, it's not enough. Because there are so many more degrees of freedom in the almost in neutral directions. But I think we can't see that right now
Mhm.
without the big discussion of periodic problems
I see.
that I want to do
So
later on.
in that problem, it's still the single eigenvectors and single eigenvalue, but it has to depend on X because it's more complicated. Is that?
Yeah, I guess I would say also, let's see, I would say, yeah, I'll just leave it at that. Yeah.
Okay, thank you so much.
Yeah. Once we have a little bit more framework for that, then it will be pretty clear why
Okay,
would be. But
yeah, thank you.
maybe I could say one thing more. If you have a periodic solution, then you have you know, something like this, and a modulation would be just change the phase. So this is W bar, say, and then you take W bar of X plus delta of X T. That's your modulation. That's just by the phase. And it allows, and it's still nearly neutral, it turns out. Not exactly neutral, because it's not, it's like taking a child's toy with a spring, and you can play around with it, you stretch it and make all kinds of shapes, right? You can compress it in one point and stretch it in another. All those are allowed here, but they're not solutions anymore. They're not exact solutions. They're just very close to exact solutions when you look closely at the analysis, and you'll see you need to allow those. But
Okay.
that's as much as I can say without saying a lot more. So I'll stop there. Stop there.
Okay. Okay. Yeah, thank you so much.
All right. So thanks everybody for coming. How's the snow over there in Bloomington? I'm curious. You have a
Super
lot?
big.
Yeah,
Yes.
I thought I heard super good from the Michigan people. Is that what you said? Super good? Okay.
It's like a foot more than
Oh, well, we have you beat by a little. A foot is like 30 centimeters. We have like almost, yeah, it's almost 2 feet. It's a lot. It's a lot. Yeah. Half of a yard. It's a foot and a half. Yeah. So thanks for tuning in on a snow day. Okay.
Bye.
Okay. So we'll see you guys later then. Bye.
See you. Thanks.
So next week I'll not be here.